All right, here's questions 5, 6, and 7. And 5 is saying it takes 208.4 kilojoules of energy to remove a mole of electrons from an atom on the surface of rubidium metal. So if you supply that much energy, you can remove 1 mole of electrons off rubidium, which would make it have a +1 charge. How much energy does it take to remove a single electron from an atom on the surface of rubidium, and what is the maximum wavelength of light that can do this? So let's take our 208.4 kilojoules. That is per 1 mole of electrons. And let's go one mole is 6.02 times 10 to the 23rd electrons. A mole of electrons is that, so those labels will cancel. And let's say that a kilojoule is 1,000 joules. I'll probably put it into joules. So when I do that, I get an answer of 3.461 times 10 to the negative 19th joules. That's how much energy it would take to remove 1 single electron from 1 rubidium atom. So it takes this much energy in kilojoules to remove a mole of electrons from a mole of atoms. It takes this many joules, really, really small number, to remove 1 electron. So there's one answer. The wavelength of light then, that would be capable of that. We can go here and solve for wavelength. Remember, these two are constants. So we can plug this energy in out in front. So we can go 3.461 times 10 to the negative 19th joules. It doesn't need to be in joules because Planck's constant in joules. 6.626 times 10 to the negative 34th times the speed of light, 2.998, or you can probably just do 3 times 10 to the 8th, all over that. To get an answer to this, I would cross multiply and divide. So you're going to multiply these two, divide by that. Wavelength ends up being 5.73 times 10 to the negative 7th meters, which is actually 573 nanometers. If you look at a spectrum of light, that is yellow light. So anything with that wavelength and smaller would have enough energy to remove electrons from that rubidium. Anything with that wavelength and smaller, because smaller wavelengths have more energy. All right. Next couple here, this is giving you a wavelength. It wants to know the frequency. So you can go here, wavelength times frequency, and solve. I'm just going to give you an answer here. The frequency there ends up being 5.77 times 10 to the 14th hertz. Last one, it's giving you an energy. It wants to know the wavelength, so we can go here. Just like we did up there, you're going to plug in Planck's constant. You're going to plug in this, put the energy out in front, and solve for wavelength. The wavelength there ends up being 2.76 times 10 to the negative 7th meters, or 276 nanometers.